All right. Hi, everyone. Welcome to the director's version of lecture 12. And now we're going to talk about applications of linear programming duality in bipartite problems, right? So this is where theory helps theory. Okay, so in the bipartite matching problem, right? So we're given a bipartite graph, and then we have the left vertices and the right vertices, right? That's why it's partitioning left and right, and the edge is set. And the question is, does it have a perfect matching, right? We saw this in lecture 7. All right, and we saw also in lecture 7 that we can randomly isolate a perfect matching if one exists, right? So, and this is great because as I mentioned to you, like this gives us fast parallel algorithms for computing perfect matchings, right? So this is really important, and we can do this also concurrently, right? So so this is an important problem. Now the question is, well, you know, there we had we were using randomness, and somehow like we had to deal with the randomness in many situations, right? So and in computer science in general, we wonder if randomness is always necessary, right? So if we removed it, then we would have a fast deterministic parallel algorithm for matching. All right. So, and this is a breakthrough result of Fandor, Gujar, and Tirov, like in 2016, but because of the journal, in the journal version was from 2 years ago. And we're going to see just a piece of the proof that uses like linear programming duality, right? For a cool fact. All right. So bipartite matching, okay, has a companion which is called circulation. Okay. So, and what is a circulation? If I give you a graph, okay, and I give you a cycle, by the way, since my graph is bipartite, I know I don't have odd cycles, right? So all the cycles are going to be of even length, okay? So given an even cycle of my graph, we can define the circulation of the cycle just by saying, well, you know, suppose that I have my cycle here. Oops, sorry. I want orange. All right, suppose that I have my cycle here, and then what I'm going to do is I'm going to draw the cycle like this with two colors. Let's say, and why is that? It's just because if I have like E1, E2, E3, E4, E5, let's say E6, for this cycle, I can define its circulation to be, you know, and these edges, they have weights, right? So we have like the weight of the edge 1, the weight of the edge 2, and so on. So if I take this alternating sum and I take the absolute value, I get what is called the circulation of the cycle. Okay? Okay, so then, now, here's a lemma, okay? So if we assign weights, suppose that I'm giving you, because remember, in the bipartite matching problem, our graph is unweighted, right? We just want to say if it has a perfect matching or not, okay? So, and the lemma is the following. If we assign weights to the edges such that the circulation of any even cycle of my bipartite graph, okay, is different from 0, then we get that the minimum weight perfect matching is unique. Does that make sense? So that's the result, right? Because how do we prove this? This lemma is not hard, okay? So how do you prove this? The way to prove it is just look at two perfect matchings, right? So if your perfect matchings are different, right? And let's say that they have minimum weight. Well, here's the thing. If let's draw the perfect matching again. Suppose that there is your perfect matching like that has these 3 edges, and the other perfect matching that you're considering has these 3 edges, right? Like they will form a cycle. Whenever they're different, they will form a cycle, right? So if the perfect matchings are different, you will have a cycle like that, which is called an alternating cycle. Now, the thing is, if the circulation of the cycle is different from 0, remember, these guys are the positive part, and these guys are the negative part of the cycle. So if it's different from 0, instead of taking the absolute value of the circulation, just look at the circulation with the sign. If the circulation is positive, then it means that the orange is bigger than like the black. But then if the orange is bigger than the black, in the perfect matching, which was orange, we can swap the orange matching by the black matching and decrease the weight. So this contradicts the fact that the two perfect matchings had minimum weight. Does that make sense? So that's the connection between circulation and bipartite matching. So it's quite an easy and really cute connection, right? That if the circulations are all different, then we know that the perfect matching is unique. So what are we going to do? We're going to try to come up with the weight assignment, okay? So, and that's what Fenner, Gujar, and Tirov did, right? They're just going to have a scheme to create this weight assignment so that all the circulations are different from zero, okay? And all right, and this is the approach, right? So now what they do, they're like, well, they cannot handle all the cycles at once, okay? All the even cycles at once, because, you know, the way like size matters here for them, right? Like we don't know if it matters in general, but for them it matters. Like that, you know, cycles that are small, like let's say of length 4 or 6 or 8, they're much easier to deal with than cycles of length, you know, like square root 10 or, you know, n over 10 or something, right? So then what they do is they're gonna construct not one weight, but they're gonna construct like their final weight will be a composition of a bunch of weights. And what they do is like they construct weight assignments that will kill small cycles. So first they're gonna say, you know what, let's kill the cycles of length up to like 8 or something, right? Let's come up with a weight assignment that kills all these cycles. And what do I mean by kill the cycle? I mean that I make the circulation non-zero. Once I do that, I save this weight assignment that kills these cycles, and then I go, and then from this, I quote unquote construct. I mean, you don't really construct because you cannot construct it, or we don't know a way to construct it. But what you do is imagine like the first weight assignment will make your bipartite graph into a new bipartite graph. And what is the new bipartite graph? Is the bipartite graph that has circulation. Okay, so what happens when you kill, okay, I'm just gonna give an outline of the paper and I'm just gonna show the linear programming part, right? So the outline here is, okay, we have a weight assignment that kills the small cycles. Now, what do they do? What they do is, oh, if I kill all these cycles, what I can do is I can consider another graph, okay, that is still composed of a subset of the perfect match of the matchings in the original graph, right? But this new graph, what they do is this new graph that we're going to study, but we cannot construct, or we don't know how to construct, is a graph that has all the perfect is a graph that does not have small cycles anymore. Okay, because this weight assignment that we assign to our graph, it already like handled the small cycles. So what they do is they construct another graph, which does not have cycles of length like up to 8, let's say. Okay, and once you do that, what they do now is like, oh, you know what? Like now that I have like handled the weights all the way up to 8, in this new graph does not have any cycle of length smaller than 8. So now let's handle all the weights between 8 and 16, right? So that's what they do. Once we have this bipartite graph with no cycles of length 2k, then in the next iteration, we kill the cycles of length up to 4k. So you can see that if we keep going this way, all we need is to do like log n iterations, right? And then we're going to kill all the cycles, right? And then we have to put everything together. Does that make sense? So, okay. So then their idea is this: we're just going to handle these cycles like, you know, at a time. Now, okay. But now the thing is, well, you may ask, well, but if I don't have any cycle of length 8, like the problem is that there may be too many cycles still of length like 16, right? So how do we handle those? Well, what happened is that they also prove that we can show that if a bipartite graph has no cycles of length up to 2k, then it actually has very few cycles of length 4k. And if you remember, this is very similar in spirit. Like this result is very similar in spirit to the min cut lemma of Karger that says like, if my min cut is alpha, then there is like O of n to the 2 alpha, like cuts of size bounded by less than or equal than 2 alpha, right? And actually, it's so similar that one may wonder if there is a connection because they prove exactly the same bound, okay, than Karger does, okay? So, okay, but now, and so this is the approach. So far, so good? Okay, and now, where does linear program enter, right? So let's study, like, suppose that we have a weight assignment W, okay? And now, given any weight assignment W, because remember, the idea that they have is we're gonna pick a weight assignment that kills the small cycles, right? So, but suppose now that we have any weight assignment, and the thing is, let G of W be the subgraph of G. And what I mean by subgraph, I just take the edges of G. I have the same vertex set, but now the edges of this new graph, they are, if an edge appears in a min W weight perfect matching in G, I add this edge to my graph GW. Does that make sense? So what I'm doing here is like, let's say, I should have an example for this, right? Like, so let me see if I can do an example here. So suppose that this is a, let's say, a weight assignment, and I have weights 1, 1, 1, and then I also did another weight, which is 1, 1, 1, right? Like, so there's these two matchings, right? Like this guy is counted twice, right? So now, and let's say that the other edges have weight bigger than 1. Okay, so this is the complete graph, but all the other edges like have weight bigger than 1, right? So then, and my graph G was the complete graph, right? So this is G. But then with the assignment W that we have here, right? Like this becomes GW. Does that make sense? Because I'm only taking the minimum weight perfect matchings with respect to W, and I'm like only picking those edges, okay? And there's no repetition in the edge, right? So for example, this edge here will only appear once, right? I'm just taking the union. Does that make sense? So this is the graph GW. Now, here's the thing. The claim is that the circulation of each event cycle of this new graph is 0. Okay, and how do we prove this? So the way to prove this is the following, right? LP duality. What we're going to use is we're going to use complementary slackness. Okay, so how do we do that? Well, okay, so what is the linear program for the bipartite matching problem, right? So this is a linear program for the bipartite matching. With weights, like with weights W, right? Like with weight W. So my primal program is we're going to minimize the weight of the matching, right? So this is minimize weight of matching. And XE is going to be like greater or equal to 0. And XE is essentially capturing that we're going to pick one matching, one perfect matching, right? So this XE is greater or equal to 0. And we know that for every vertex, okay, we will take one edge, right? Because that's the matching condition, right? Now, you may be wondering, well, Rafael, shouldn't I have put here that XE is in 0, 1 for every edge, because the x's can be fractional, correct? But the thing is, well, we don't need this condition because of the Birkhoff-von Neumann theorem. Which tells us that all the vertices of this polytope, they're integral. Okay, so we don't need to enforce this condition. Okay, so that's why we have a linear program. And well, we're going to see next week like linear program relaxation. So you're going to see how this pops up again. We're going to mention this polytope again, right? This is a pretty interesting polytope. Okay, so we have this linear program, right? And now we know that it's a true linear program. Now, what is the dual of this linear program? If you compute the duality of this linear program, notice that it is in standard form. So the dual of this program is exactly this. Okay, so for each, and remember, like if you want to do like duality, you know that for each prime of variable corresponds like a dual constraint, right? So the dual constraint for the variable xe is this one. So each edge has a constraint. The new variables are the variables yu, where u is the vertex, right? And this is the dual. So if you just do the duality, you get this other program. And now, what does complementary slackness tell us? Complementary slackness says that if xe is different from 0 in a prime, suppose that x, okay, so complementary slackness, here we're assuming that xy is a primal dual solution, right? Like is a optimal solution, optimal primal dual pair. Right? So now complementary slackness says that, you know, if I look at an optimal solution and this xe is different from 0 in the primal, then the corresponding dual constraint is tight. But what does it mean that the dual constraint is tight? Well, it means that yu plus yv is equal to we. Right? And now, okay, so what do we do? Well, now, if we look at the, let's look at a cycle from the bipartite graph, right? So this is in GW. Let's look at a cycle in GW. So this is going to be like U1, U2, U3, U4, U5, U6, right? And what we want to say is that let's look at the circulation of this graph. What is the circulation? I will have like weight 1, 2, weight 2, 3, weight 3, 4, weight 4, 5, weight 5, 6, weight 6, 1, right? But the thing is, remember, if this edge is included, it means that x of this edge is different from 0, right? So in particular, in the dual, what we have is that, you know, we have that y1, y2, y3, we have these variables, right? Like y4, y5, y6. In the dual, we have those variables. But now, if those edges appear in GW, it means that xe is different from 0, which means that wij is equal to yi plus yj. Right? By complementary slackness. Now, here's the thing, right? Once this happens, right? What can we say? Well, but now do the sum, do the alternating sum. Like if we do the sum here, what do we get? We get exactly like W12 minus W23 plus W34 minus W45 plus W56 minus W61. What is this? This is exactly y1 plus y2 minus y2 minus y3 plus y3 plus y4 minus y4 minus y5 plus y5 plus y6 minus y6 minus y1, which is exactly 0. Does that make sense? So, okay, so that's pretty much it. Right, that's the proof. It's a pretty slick proof. Is that any questions?